Welcome back to physics, everyone. So today we have myself, Ms. Sundar, and also Mr. Hatzfeld joining us. We're teaming up to talk to you about modern physics. So throughout the year we have studied, for most of the year we studied matter, and then we started looking at waves. So in waves we saw sound, we saw light, and today our first section of modern physics we're looking at wave-particle duality, how sometimes matter and light can behave as a wave, and sometimes it can behave as a particle. Mr. Hatzfeld?
At this point in our study of physics, it's important to ask those what seem like simple questions. Things like, well, what really is light? And what really is stuff? And now we have the tools to really discuss what these things truly are. Since we discussed objects, we discussed waves, we could discuss what categories do these things fall into. And we're going to start our discussion with what light truly is at the most fundamental level. We've been just kind of assuming that light is a wave. We said light is a wave, but how do we know for sure that light can behave as a wave? There is very strong evidence that light behaves as a wave. What are some things that waves do? We learned about wave phenomena, right? We learned that light does some things like it could interfere with itself, and it could diffract. And objects don't do those things. When we talk about interference, we know that two things are occupying the same space at the same time. And I don't know about you, Ms. Sundar, but I haven't seen any objects occupy the same space at the same time.
As far as objects go, they really can't do that. So only waves have that ability to be able to not only occupy the same space at the same time, but they can add together or subtract from each other. And that is the phenomenon which we know as interference. So another behavior which only waves can exhibit, as Mr. Hatzfeld mentioned, is the behavior of diffraction. So remember, diffraction is that spreading of the wave through an opening or around an obstacle. And as far as we know, if we throw a tennis ball at a wall, it's not going to spread around the wall, it's only going to bounce off the wall. So objects can reflect, but they cannot diffract. And because light can diffract, it must be a wave.
Yeah. And this evidence of interference and diffraction convinced us without a shadow of a doubt that light is a wave. Because like Ms. Sundar said, we don't see objects doing these things. We had a really robust mathematical model for describing light as a wave, and everything was working really well for a long period of time. And then we got into modern physics, which made things a little confusing for us. The wave nature of light was working for a really long time, but then we started running into experimental examples of the wave nature of light not really doing a good job of explaining what we observe in nature.
So one of these experiments, which could not be explained using the wave theory of light, was the photoelectric effect. So Albert Einstein, who I'm sure you have all heard of, won his Nobel Prize in Physics for his explanation of the photoelectric effect. Even though he's most famous for and most well known for his theory of relativity, it's the photoelectric effect which actually won him that Nobel Prize. Mr. Hatzfeld?
So we want to discuss the photoelectric effect and why the wave nature of light does not well explain what the what we observe with the photoelectric effect. But before we can talk about that, we have to talk about what the photoelectric effect truly is. Something I like to do is like to break down these words because the definition of these words are often right there in the vocabulary. Photo is the prefix for light, and electric is quite literally electric. It's an effect that light has on electrical phenomena. So we found out that when a metal is illuminated by light, the metal may emit electrons. Now, we learned through our study of circuits that when electrons are emitted and start moving around, we have electrical phenomena. We get circuits working this way. And this is pretty interesting because all we need to do to emit and get electrons moving is just shine a light on a particular metal.
But it can't be any light, can it?
It cannot be any light, and that's something that we definitely need to talk about. And this is what where the big mystery came for how the photoelectric effect truly works.
So let's take a look at what this photoelectric effect experiment actually looks like. So here we have a setup for our photoelectric effect experiment. We have a light and we have what's called a target. So this is some kind of metal. In this case, we are using sodium. And we're going to shine the light on this metal and we're going to see what happens. So right now my intensity is set at 0, which means intensity refers to the brightness of the light. So right now my brightness is at 0%, and I'm going to slowly increase that intensity of light. So we're in the red region of our electromagnetic spectrum. And notice, no matter how bright we make that light, nothing happens.
Now that's interesting, Ms. Sundar, because intensity would have to do with like the amplitude of the light wave, right?
Right. So in classical wave theory, that amplitude of the wave correlates to the energy carried by the wave, but here it seems to not do anything by changing that intensity. So let's see what happens if we change the color or the frequency of light. So from red, I'm going to go to shorter wavelengths, higher frequency. So now we're in the orange. Now we're in the yellow. Transitioning towards green. Still nothing. Still nothing. And I can test it again to make sure my intensity, again, even at 100% intensity, this green light is doing nothing for the sodium. So let's keep going to higher and higher frequencies. Something's
I
happening.
see something.
So now that sodium is emitting electrons because of that light which is shining on it. If I keep increasing my frequency, let's see what happens to those electrons.
Now we're into blue, we're into purple. It looks to me that those electrons are moving quicker.
Quicker, faster, which must mean they have more energy?
More energy. Sounds right to me.
So the higher we make the frequency, so now we're in the UV, ultraviolet. So you see as we go to higher frequencies, those photoelectrons are getting faster and faster. So you can see there's some correlation between the frequency of light and the energies of these ejected electrons.
Now, when we learned about electromagnetic waves, we said that the energy of the electromagnetic wave was directly related to the frequency of the wave. But we didn't say exactly what evidence we have to support that. And the photoelectric effect is a great example of the frequency of the light on the metal increasing the energy of the electrons. The light has a direct effect to what kind of energy the electrons have. A higher energy light is giving the electrons more energy through that tube. Now, Ms. Sundar, what happens when we vary the intensity once those electrons are actually moving?
Let's test it out. So now I'm at 73% intensity. Let's try lowering it, see what happens. I'm going to lower that intensity.
The intensity is directly related to the amplitude of the electromagnetic wave.
So if you look now, our photoelectrons are still pretty much moving at the same speed, but there are fewer of them being kicked off of that sodium, right? And if I increase the intensity, I'm going to go all the way up to 100. So again, same speed, same energy, but there are more of these electrons which are being ejected from that sodium. So let's summarize our findings from this photoelectric effect experiment. So as we saw in the demonstration, electrons were only emitted when the light reaches a certain minimum frequency. If we didn't hit that threshold frequency, nothing happened.
So eventually, once we reached that minimum frequency, that's when the electrons started getting kicked off that metal. And we saw that as once the electrons were actually moving, when we increased the intensity of the light, all it did was increase the number of electrons being emitted, but it did not increase the energy of those electrons being emitted. That's very important. When light is below that minimum frequency, no matter how intense it is, we can make that amplitude super high. No electrons are emitted. So the fact that electrons get emitted and what kind of energy they have depends solely on the frequency of the light striking that metal.
And this is where light is different from other waves, such as mechanical waves, because for a mechanical wave, we know that the energy corresponds to the amplitude of the wave, whereas here we see that's clearly not the case. So we need another way to think of light.
And I can't undersell this enough. This was blowing scientists' minds at the time. We were certain that light behaved as a wave, but this experiment proves, and the best way to explain what's going on in this experiment is if we look at light as behaving as a particle, not as a wave.
So each particle of light, we have a name for it. A particle of light is called a photon. So we say that each quantum, a quantum means a packet or a particle, it's like a little bundle, and each bundle of this light, like I said, is known as a photon. Again, you see that word photo, that root in there. Photo refers to anything having to do with light.
So basically, because we have to discuss light as a particle, we're putting a name to it. But it didn't really still solve that mystery of light behaving like a wave in some cases and like a particle in other quick cases. So we're going to define photon, and we'll return back to that discussion of what is really going on with light.
So the energy carried by this photon is directly proportional to its frequency, as we saw in the demonstration. So we can describe this using an equation. So we can say that our energy, E, is equal to some constant of proportionality, which we're going to call H, times our frequency, F. So in this equation here, energy has to be in units of joules. F, our frequency, has to be in units of hertz. And H is a constant, which is known as Planck's constant, which has a value of 6.63 times 10 to the negative 34 joule
34?
seconds. Negative 34.
That's tiny, Miss Sundar.
And the units on that constant are in joule seconds to make sure that our units all work out in the equation.
Why is it joules times seconds if frequency is measured in hertz?
Well, a hertz is a cycle per second, or we can say 1 over seconds. So we need to make sure we get joules on this side of the equation. We have to cancel out or divide out the second in the denominator here, since this is 1 over seconds, which means our constant is going to have units of joules times seconds.
That makes sense. So back when we were still dealing with these concepts of seeing that the photoelectric effect is best described with the particle and how all these theoretical issues we were having, a man by the name of Max Planck, a German physicist, he did something that was very against his nature. It actually drove him nuts at this time and for the rest of his life. He said the only way that we could describe what's going on here is if we start to discuss light as a quanta, as a particle. So he was the first person to make that idea leap, to say that light is behaving as a quantum, as a photon. And it's something he struggled with for the rest of his life. He started the quantum revolution, and he spent the rest of his life fighting against the quantum revolution. We said that Einstein was the one who put everything together with the photoelectric effect. Einstein connected the dots between Planck's light quanta and using that to explain what exactly is going on with the photoelectric effect, and that's what earned him the Nobel Prize.
And just to give you an idea about when this is all happening, we call this modern physics. So we're looking at the time period from about 1900 onwards. So it's modern in the sense of the history of physics, but still this happened more than 100 years ago. Now, we can calculate the energy of a photon if we know the frequency of light we're dealing with. But we also can measure another property of that light, which is its wavelength. we know there's a relationship between the frequency and the wavelength of light. So we know that for light, the speed of light, c, is equal to your frequency times your wavelength, which means solving for our frequency, f, should equal the speed of light divided by the wavelength. So there are two ways in which we can calculate the energy of a photon. We can say that E equals hf, or if we don't know the frequency of light but we know its wavelength, we can also say E equals hc over lambda, where that c is that speed of light in a vacuum, 3 times 10 to the 8th meters per second. So let's try some examples and see how we would use these equations. So example number 1, what is the energy of a photon that has a frequency of 5.09 times 10 to the 14th hertz? And we want to know what kind of photon is this? Where on the electromagnetic spectrum can this photon be found?
So we get to finally use that new equation that we just learned. E equals h times f, Planck's constant times the frequency. So the frequency is given right there in the question, 5.09 times 10 to the 14th hertz. And all important physics constants you should know is on the front page of the reference table. You can find Planck's constant there, no need to memorize it. So let's just plug it right in. We have Planck's constant from page 1. That is 6.63 times 10 to the negative 34 joule seconds, multiplied by 5.09 times 10 to the 14th hertz. And when we plug that into our calculator, being very careful with our scientific notation, we get an answer of 3.37 times 10 to the minus 19th joules. So we have the energy of this photon. It's not very high, 10 to the minus 19 joules. We're on the order of electron volts here. So the next part of the question, we want to find where on the electromagnetic spectrum can this photon be found. So what we're going to have to do is we're going to look at our electromagnetic spectrum in our reference table, and we have a frequency. So we could use that frequency to identify exactly where this photon should be found on our reference table. When you look closely, this 5.09 times 10 to the 14th falls within the range of yellow visible light, which is pretty cool. So based on the information given, this photon we would interpret as yellow visible light.
In our second example, we are asked what is the energy of a photon that has a wavelength of 350 nanometers, and again we want to find out what kind of photon is it? Where does it fall in the electromagnetic spectrum? So notice in this situation we were not given the frequency, but we were only given the wavelength of this photon. So we can use the other version of our equation. So we can say that E equals hc over lambda, and again h is that same constant, 6.63 times 10 to the negative 34 joule seconds. C is also a constant, it's always going to have the same value of 3 times 10 to the 8th meters per second, and lambda, when we substitute into the equation, must be in units of meters. So nano is the metric prefix, which stands for 10 to the negative 9th, so we're going to substitute this as 350 times 10 to the negative 9th meters. So now that we have all our information, we can substitute that into our equation, and putting it into our calculators, we will solve and get that the energy comes out to 5.68 times 10 to the negative 19 joules. And again, as Mr. Hatzfeld mentioned, we are on the scale of electron volts. And going back and looking at your electromagnetic spectrum, which you'll find either in the reference table or in your notes, we find that this is a photon of ultraviolet light. So let's talk about some other properties of these photons.
So photons are super strange. Some of the properties of photons, one of the most mind-bending parts of photons is that photons do not have mass whatsoever. They are particles that are massless. They are massless particles, but these particles do carry momentum. So photons have momentum, but no mass. How do you square that circle, Ms. Sundar?
In classical mechanics, we define momentum as m times v, mass times velocity. But now, in this case, a photon has no mass, but it does have a momentum.
So even though these photons have no mass, we know they have momentum due to studying how these photons collide with other particles. When a photon collides with a particle, the energy and momentum of the photon is conserved. One of the core rules of physics that we always have to make sure we're following is that momentum and energy are always conserved. Even in this weird realm of modern physics, those are some of our anchors that keep us sane through this crazy study.
So let's say we have a photon colliding with a stationary particle. In this situation, the energy and the momentum of the photon will decrease while the energy and momentum of the particle will increase. So this photon is passing on or transferring some of its energy and momentum to that particle. And as Mr. Hatzfeld said, just like we would expect in all other situations, your energy and momentum are going to be conserved. So if we have a situation where we have a photon which is colliding with this particle which is initially at rest. After the collision, this particle is going to take off with some energy and momentum, and this photon we say is going to be scattered. And notice that this scattered photon, initially, it has a small wavelength, meaning it's of a higher frequency. Higher frequency is going to mean it has more energy and more momentum in this situation here. And our scattered photon, you can visibly see it has a longer wavelength. It is also shifted to red, which means it has a lower frequency because it has given up some of its energy and momentum to this particle, which is now taking off with some amount of kinetic energy. So this phenomenon here, this collision between this photon and this particle, this is known as the Compton effect or Compton scattering. So this is something which has been observed and measured, and we know this is what actually happens.
So this all just kind of seems strange. It still doesn't really sit with me that well. Like, we're talking about particles, but we're talking about the wavelength of these particles and the frequency of these particles, which tells us that these photons are following that idea of wave-particle duality. Under certain circumstances, they act like particles. Under other circumstances, they act as waves. And we can use both those ideas to better describe what's going on with these photons. But it's not only light that exhibits this wave-particle duality.
So the big question that came up was, what makes light so special in that only light can be both a wave and a particle? After all, light is part of the universe just like everything else is part of the universe, so why should only light have this wave-particle duality? Why not everything else in the universe? Why can't matter be a wave and a particle as well?
So a guy by the name of Louis de Broglie, I don't know how to say his name, but he proposed that all matter has both a particle and a wave nature, which is really interesting. So now we're looking beyond light having a wave-particle duality, but matter particles, he proposed, also have a wave-particle duality.
So Mr. Hatzfeld, are you saying that you and I are waves?
I'm saying that we are relatively large, slow-moving particles. If we take these matter particles at the atomic scale or the quantum scale and move them at very fast speeds, they clearly exhibit this wave nature. At our scales, our wavelengths are too small to see any of this wave nature apparent in our daily lives.
So the wave nature of matter is not apparent on the macroscopic scale. So in our everyday lives, we don't see baseballs and trucks and people behaving as waves. But when we zoom down and look at the really, really tiny particles moving at high speeds, on the atomic scale, we can observe this wave nature. So what kind of wave nature are we referring to? Earlier, we talked about how we knew that light was a wave. And one of the experiments that proved that was Young's double slit experiment. So these diagrams and this animation here shows what happened in Young's double slit experiment.
So let me just briefly describe what's going on with this experiment. On the left diagram, you can see that we're sending in some kind of wave to this black barrier. And if you look closely, in that barrier, there are two locations where the light or whatever wave we're sending in can pass through the barrier. Now, this is a great experiment to prove whether something is acting like a wave or a particle. Because if something was acting like a particle, it should just pass through that opening, and then on the viewing screen, we would just see two slits, two bars of where those particles pass through and hit the viewing screen. But if something acts like a wave, it'll diffract and interfere with itself, creating this interference pattern that you see on the left. So when we send light through this double slit, we see that light acts like a wave because we see the interference pattern on the viewing screen. But here's the thing. If we do the same experiment with electrons moving at relatively high speeds, and we pass those electrons through those slits, we actually see a diffraction/interference pattern on the viewing screen.
So like Mr. Hatzfeld mentioned, we can observe the diffraction and the interference of electrons. So here we have a similar experiment as to what we did with light. So we're going to take this beam of electrons and pass it through these double slits. Now, if these were behaving like particles, let's say like I threw tennis balls through these two slits, we would expect to see just a bunch of tennis balls hitting the screen over here in front of the first slit and a bunch of tennis balls hitting the screen in front of the other slit. But in fact, what happens is we get an interference pattern. We get locations with lots of electrons, no electrons, lots of electrons, no electrons. So we get constructive and destructive interference. And here is a photograph of such an interference pattern through the crystal structure of some material. So electrons can diffract and interfere, which means they must be behaving like waves.
So here's one of the coolest things about modern physics. It makes us really question things that we take for granted every single day. This idea of wave-particle duality is very counterintuitive. It's not something we experience at our scales. Let me leave you with this thought. So if we repeat the experiment, like we talked about before, sending those electrons through the double slit, we do see that interference pattern. But I'm going to change the experiment slightly. I'm actually going to put a measuring device right at the double slit so we can observe those electrons as they pass through. The only thing we're changing about this experiment is we're observing the electrons as they pass through the slits. Everything else is the same. And what's really interesting by repeating the experiment in this way is when we send those electrons through the slits and we observe them going through the slits, then the viewing screen shows that they're acting just like particles. There's only two bars where the electrons pass through the slits and hit the viewing screen just like we were throwing tennis balls through these screens. And the only thing we change about the experiment is we observe the electrons as they pass through. Observation and measurement plays a critical role when we're talking about quantum mechanics. It's one of the really strange things when we're talking about things at this scale. I really enjoyed this type of discussion, and we will continue this discussion with some future videos with some other modern ideas. I really enjoyed doing this lesson with you, Ms. Sundar. This was cool.
Yeah, this was fun. So
All
see
right,
you guys
everybody.
next time.
Yes. We'll see you in the next video.